Hello and welcome to our second lecture in this course on string theory. As you might have seen, since last time I have updated the bibliography with a few more textbooks. And in the course forum, you can find a thread where I've made a few comments about each of the textbooks, which might help you to find a suitable one for you. I've also uploaded the extra sketches that I used during the first lecture. Will always do this. The slides themselves will always be available in advance. I do not necessarily expect that you look at them before, but I would like to give you the opportunity. If you like to use them in advance, then you can do this. Now, last time, we discussed the relativistic particle and started a little bit to talk about the relativistic string. But before I carry on, is there any immediate question that somebody would like to ask? Good, this seems not to be the case, but since it's rather difficult for me to give the lecture and monitor the chat, if there is an urgent question, then please feel free to unmute yourself and interrupt me. Good. So let's see where we ended. Go to our first slide. So initially we talked about particles, and then we decided that we now spread out particles into strings. So, and well, when a particle moves, it describes a line, which we call the world line. So for a string, we get a surface, which we call the world sheet. And we need two coordinates to parameterize this world sheet. And our convention is such that one of the coordinate lines has a time-like tangent vector. This one tangent vector here, which I call x dot, and this is the coordinate sigma 0, which is therefore time-like, and the other coordinate line is chosen to have an everywhere space-like tangent vector, and the corresponding space-like coordinate is sigma 1. There are some normalization conventions for the world sheet time. Sigma 0, it can be any interval on the real line. But for sigma 1, which is a parameter along the string, if you like, we fix the parameter interval between 0 and pi. It's not necessary. Some books use other conventions where you keep this an arbitrary constant. But anyway, the coordinate sigma 1 does not directly measure the length of the string, which, as you will see, is dynamical. And I find this convention convenient. Good, so this has set up our conventions. Now, our first question is what kind of action principle we should use for a string. Now, the natural idea is to just generalize what we see worked for the particle. For the particle, it was the length of the world line, or as we call it because it's a time-like curve, the proper time, which was extremized. And the natural generalization is to say we take an action which is proportional to the area of the world sheet of the string. This is called the number goto action. Now, an action has a certain dimension. We are using units where we put the reduced Planck constant in the speed of light to unity. And then, if we have an area which has dimension length squared, we need a parameter of dimension 1 over length squared to make it dimensionless, as befits a unit, an action in natural units. And the better, more physical way to read this is as energy per length, which is then also known in mechanics as the tension. So this is the single independent dimensionless quantity that we assign, that we have with a string. It's its tension or energy per length. And then we have our action, we have a conventional minus sign. But now we need to remember or to learn how we measure the area of the worldsheet. And the worldsheet is an embedded surface. It is a surface which we have embedded into Minkowski space-time. And therefore, we can measure area on the surface by using the Minkowski metric on Minkowski space. Because if you have a surface, or more generally some manifold embedded into another manifold, and the manifold you embed into has a metric, then we get a metric on the embedded surface by pulling back the metrics that we have on the embedding space. The formula is given in formula number 8. So we take the metrics that we have in Minkowski space-time, contract it with our tangent vectors, and this takes as an input this d by d matrix, which represents the metric on Minkowski space, and gives us a 2 by 2 matrix G alpha beta, which is the induced metric on the worldsheet, also called the pullback metric, or differential geometry is the first fundamental form. And given a metric, I can form an invariant area element. This is formula number 9. So what I have to do is I integrate over the coordinates and weight it with the square root of the determinant of my induced metric. And since we have a surface with one space-like and one time-like direction, the determinant of the metric is negative, so I have to put a modulus in order that my root is well defined. This is my area element. Good. So we now understand our action. We note what invariance properties it has. First, and very importantly, it is invariant under reparametrization. This is, of course, important because the area of a surface should not depend on how we label the points on it. Now, these reparametrizations are genuine maps from two variables to two other variables. I've stressed this here in formula number 10. So each of the new coordinates sigma tilde alpha can depend on both the old coordinates. In order to make this a valid reparametrization, the map between old and new coordinates must be invertible. And the condition for a map between many variables to a set of other many variables is this one given here. We have to form the so-called Jacobian, which is a matrix of all mutual partial derivatives that you can take between old and new coordinates. And then the determinant of this matrix must be different from 0. This gives an invertible map. And if we require this to be positive, then even the orientation of the surface is preserved. Good. So that's important to make sure that our area and our number Groto action is defined in a meaningful way. It also has another symmetry which it inherits from Minkowski space. Namely, last time we discussed Poincaré transformations, and I've listed here again in formula 11 how Poincaré transformations act. And of course, the number Groto action must be Poincaré invariant. And you can check for both these conditions that they are satisfied. Now, let us get accustomed with the metric, with the action a bit more intimately by writing it out more explicitly. Just to make sure that you get my notation, if I write here something like x dot x prime, then I have suppressed the Lorentz indices, and it is understood that there is a Lorentz scalar product. Same, of course, with x dot squared. This is x dot mu, and so on. So wherever I think it does not lead to confusion, I will suppress Lorentz indices so that my formulas do not look too cumbersome. Now, for the following manipulations, it is helpful to introduce the momentum densities on the string worldsheet. These are the derivatives of the Lagrangian with respect to the tangent components of tangent vectors. The first value is if we put the worldsheet index alpha equals to 0, we get dl by dx dot. And this quantity is also what we call the canonical momentum, because the canonical momentum is always the derivative of the Lagrangian with respect to the generalized velocity. And velocity is the derivative of a coordinate with respect to the time parameter, which in this context is sigma 0. If you compute this explicitly, you see that this is a rather complicated expression. It looks a little bit forbidding, but we will see how to handle this later in the lecture. For a string, we also have a component of momentum density, which, so to speak, goes along the string, and that's in a similar looking expression here. Now, to already indicate that while these expressions look complicated if we are in a general coordinate system, their essential meaning is rather straightforward. Let us take a parameterization of the worldsheet such that the tangent vectors are also normalized. So x dot squared is a time-like vector, x dot squared is -1, x prime squared is 1, the two are orthogonal. If you plug this in, then you see that these momentum densities are just proportional to the tangent vectors. And now you realize that these relations are quite natural generalization of what we would have for a particle. Namely, for a particle, we would have a relation that the momentum is proportional to the velocity x dot. This is meant to be a dot here, with the proportionality factor being the mass m. Now we have two components of momentum density because you have spread out the particle into a string, and the factor of proportionality is the string tension, which plays a similar role for the string as the mass plays for the particle. An important topic which we could avoid for the particle are boundary conditions. And this comes into effect as follows. Maybe this is a good point to show you a drawing. But before saying this, just to remind ourselves, how do we get our equations of motion? We take the action, we replace the configuration x by x plus delta x, and delta x is an arbitrary but small variation, but we impose that the variation vanishes for the initial and final configuration. Now, how does this look like for a string? Maybe it's not a point where I should show you my drawing, which I think is on this sheet. Yeah. So look at the lower drawing here. What I show you in black is the propagation of a string for some amount of time. And then I add a small variation delta x in red. And while the initial and final string are, of course, the same, in between, the string can vary, including at its ends. But if one now carries this through with making a variation of the action, then one comes in the situation indicated here in function 15. We have partial derivatives acting on variations, which we have to move over by making integration by parts to get the bulk terms. And the bulk terms, which are the full integrals of both sigma 0 and sigma 1, will then give us the equations of motion. But in order that we can claim that these are the equations of motion, we must make sure that the action is really at an extremum. But because the ends of the string in intermediate worldsheet times can move, we get a boundary term. And this is this term here. And in order to have a consistent variation problem, we must insist that these boundary terms vanish. And that means that we have to impose boundary conditions. So in addition to equations of motion, we also get boundary conditions dictated to us. And now we have to decide what are the admissible boundary conditions which makes this term vanish. It turns out that there's three classes of boundary conditions that we can consider. So one obvious choice is to say, oh, we take periodic boundary conditions, which in a sense means that there is no boundary at all, and then we have a closed string. And then the worldsheet becomes a cylinder, and this does not have a boundary, and the boundary term is away, and we don't have a problem. Second choice is, if I want this boundary term here to vanish for arbitrary variation delta x, I can require that dl by dx prime, which is one of my momentum components, vanishes at the ends of the string. These are the natural or Neumann boundary conditions, and they describe open strings with freely moving endpoints. The condition that dl by dx prime vanishes, if again go to an orthonormal parameterization, this means that x prime mu is equal to 0 at the ends, and x prime is a component of the momentum flow along the string. So this boundary condition tells us that no momentum is allowed to flow off at the ends of the string. So that is the natural condition if we describe a string which freely moves around in space. The final choice that we can make is that we can say, well, we can keep the ends of the string fixed, and then, of course, this variation is by construction 0. This corresponds to the situation that we are familiar with for, say, a guitar string or a piano string or a violin string where the ends are fixed. We can fix them, for example, at two different positions, x0 and x1. Now, for a guitar string or for a musical instrument, this is quite natural. But of course, when describing natural elementary particles, it is not so obvious that this kind of boundary condition is of any use. Therefore, until the mid-90s, these types of boundary conditions were ignored, but it was then discovered that they are useful after all. So let me expand a little bit on this. With the Dirichlet boundary conditions, momentum is not anymore conserved at the endpoints, and that means that there's momentum flowing off. If we believe in momentum conservation, then this momentum must go somewhere, and that means that the points or surfaces on which such open strings end must be dynamical objects because they exchange momentum with open strings with Dirichlet boundary conditions. And these points or surfaces on which such open strings end are then the famous objects which by now we call Dirichlet branes. So the simplest example of such a Dirichlet brane is given here in the formulas 20 and 21. I impose, say, Neumann boundary conditions in time and P of the space-like directions and Dirichlet boundary conditions in the remaining space-like directions. So this corresponding D brane would then be, let me draw, just indicated by a line, but in general, this is now a p-dimensional surface, and the allowed open strings would look like this. These are the Dirichlet boundary conditions in which directions the open string cannot move, and these are the Neumann boundary conditions where the string can move. So the string can move freely as long as its ends are attached to this p-dimensional surface called a Dirichlet p-brane. Well, that is one possible choice of these boundary conditions, but I can be more general, and I think I've prepared a drawing for showing you a more general choice of these types of boundary conditions here. For example, I could decide that these are the Dirichlet, these are the Neumann directions. I could decide to have two such D branes at different points, and then I suddenly have a whole variety of different types of strings. I can have strings which are attached to the first or to the second D brane, but I can also stretch strings between the first and the second D brane. And since our strings come with an orientation, it matters whether a string starts or ends on the first brane. Now, why has this become attractive to particle physics? We will see later that we are forced to admit that space has more than the usual 3 dimensions. And then such D branes come in useful because you can imagine by distributing D branes at certain points in space, I can control how the excitation spectrum of string states looks like. And by being very clever in distributing d-branes along the extra dimensions, I can engineer an excitation spectrum which has desired properties. For example, I can try to make this more and more similar to the standard model of particle physics. And this way, d-brane engineering and d-brane model building occurred. And this is one of the major uses that d-branes have by now. That's why they are important. So at first, one might think that for particle physics, this is no good. Okay, let's return to the slide. That was, I think, what I wanted to say about d-branes at this point. Yeah, there's one further question that one might ask, namely, does it make sense to impose Dirichlet boundary condition in time? At first, it doesn't make sense because it would mean that there's a kind of d-brane which only exists at one moment or one instant of time. However, the word instant might, by association, bring in the word instanton, if you have heard about this in another course already. And briefly explaining what instantons are. If one uses the so-called Euclidean formulation of a theory, where one makes time imaginary, then instantons are configurations of the Euclidean version, which are non-trivial solutions to the equations of motion. And these instantons describe effects in the associated theory in Lorentz signature, which are not detectable in perturbation theory and which are very important. Therefore, one way in which Dirichlet boundary conditions in time are used in string theory is in the context of this Euclidean formulation of the theory, where time then is on the same footing anyway as any of the spatial directions, and there then are so-called d-instantons. There is a more unconventional use, proposed use of Dirichlet boundary conditions. Some people even think that it makes sense to really impose Dirichlet boundary condition in time if you are really in the physical spacetime with Lorentz signature. These event-like branes are called sometimes S-branes, or in other contexts, E-branes. They're kind of Lorentz signature analogs of instantons. So they correspond to events, and one obvious potential application of this is cosmology, where an event could be a situation where you have an initial or final singularity. But this use of Dirichlet boundary condition in Lorentz signature is a little bit less standard, whereas using Dirichlet boundary conditions in imaginary time to describe instantons is quite an established technique. So a bit more advanced than we will be able to discuss in these lectures. Okay, I think that now finishes what I wanted to say about d-branes today. And now, with the boundary conditions sorted, we can go to the equations of motion, which come then from the vanishing of the bulk terms of our variation. Using our momentum densities on the worldsheet, we can write the equation of motion in a concise form, this formula 22. And of course, if we would now write it out in general coordinates, it would look rather complicated because these momentum densities look rather complicated. And we will come back to how to handle this. At this point, we want to make some structural observations, which we can draw from this generic form of the equations of motion. Namely, we can come back to the topic of constraints. For the point particle, we saw that the kinetic momentum was equal to the canonical momentum, and therefore the components of canonical equals kinetic momentum were not independent but subject to a constraint in the mass shell condition. Now this generalizes again to string theory, because you can show that this time there are two constraints. One is formula 24, which, since it involves the square of the canonical momentum, looks a little bit similar to the mass shell condition. and the other is an orthogonality condition between the canonical momentum and the space-like tangent vector. These are the two independent constraints, and you can verify, I suggest this as an exercise, you can verify that these two constraints hold, and in demonstrating them, you do not need to use the equations of motion, so these are off-shell conditions. Off-shell always means without using the equations of motion. These are the two independent relations, but you can get other relations using them. In particular, if you compute the canonical Hamiltonian by making a Legendre transform of the Lagrangian, you find that the canonical Hamiltonian is equal to 0. This was the same observation that we made for the relativistic particle, and as I explained, this is to be understood as a constraint, that is a condition which we have to impose on top of the equations of motion. And it's absolutely generic for manifestly covariant formulations of relativistic theories. And we will see how to handle these constraints further down in the course. Now, while we don't want to go into details of how to solve the equations of motion, yet I remark that things are not as hopeless as they might seem if you remember these complicated expressions for the momentum densities, because if you again go to special coordinates where you orthonormalize your tangent vectors, this equation reduces to something simple, named the two-dimensional wave equation, for which, of course, the general solution is known from D'Alembert. Not all solutions of the wave equations will correspond to physical configurations of strings, because, as we have seen, we need to impose in addition boundary conditions, and we have to find a way of imposing our constraints too. But before coming to how to do this, I would like to introduce to you a second action principle for strings, the so-called Poldyakov's action. The Poldyakov's action works as follows. The first step that we take is that we introduce an auxiliary variable similar to the auxiliary variable E in the third action principle that we discussed last time for the relativistic particle. And this auxiliary variable can be viewed as an intrinsic metric on the worldsheet sigma, again with a Lorentz sectional, this time a two-dimensional signature. And string theory is now formulated in terms of maps, which map two Riemannian manifolds, pseudo-Riemannian, because we admit indefinite metrics, to each other, the worldsheet with its independent worldsheet metric H, and space-time with its Minkowski metric. Again, that might be helpful to give you a drawing. So here, in this picture, we see in blue the string worldsheet sigma, which I've drawn as a strip. With periodic boundary conditions, the strip would become a cylinder. And this has now been equipped with a two-dimensional metric H alpha beta, which is completely unrelated to the Minkowski metric that we have in space-time M, which is drawn here in black, and into which the string worldsheet is embedded. And the coordinates x mu of the string precisely tell us how a given point on the worldsheet maps to a given point, or maps to a point in Minkowski space-time. Now, given this embedding, as we used for the number go-to action, we can take the Minkowski metric and pull it back to get this induced or pullback metric or first fundamental form G alpha beta. But G alpha beta is, of course, at this point, completely unrelated to H alpha beta. No? G alpha beta is determined by eta mu as soon as we know X, whereas H alpha beta is something which we can take completely independently. And it will be the equations of motion which tell us how these objects are related to each other. Okay, let's go back to the main slides now. I think I want to be here, right? Pick the right page. So let me now just state how the Polyakov action looks like. It's given by formula 28. This is in fact a standard formula, both in physics and in differential geometry. Physicists call such type of action a sigma model, whereas for differential geometers, this is the energy functional for a map between two Riemannian spaces. So we have as a prefactor again the string tension. Then we have here, we see the tangent vectors contracted with the Lorentz indices contracted with the Minkowski metric, the worldsheet indices contracted with the inverse of the worldsheet metric here. And then we have the square root of the determinant of the worldsheet metric, where again we have to take the absolute value. Well, the first thing is to make sure that this action is well defined, which means that we must check that it's invariant under reparametrizations, which again I suggest to do as an exercise. But to help with this, let me clarify one point which is potentially confusing. The string coordinates x carry an index mu, but this index mu refers to Minkowski space-time and to the Lorentz transformations acting on space-time. With regard to the worldsheet, each x mu is just a function of scalar field and therefore transforms as indicated under reparametrizations. In contrast, the worldsheet metric is a covariant symmetric second-rank tensor, and therefore it transforms accordingly under worldsheet reparametrizations with the Jacobian or inverse Jacobian of the coordinate transformation acting on each index, the usual transformation behavior of a tensor. So this is reparametrizations, and this tells us that our action function is well defined. It is important here to note that it has a further local symmetry besides reparametrizations, and this is what I introduce here as a Weil transformation. I mean, what we can do is we can take the metric and multiply it by an everywhere positive function. And since this function is everywhere positive, I've parameterized this as an exponential. That is a very important observation, because this is an additional local symmetry that we have for this action principle. And finally, it's also Poincaré invariant, which should be clear from the way how the indices are contracted with each other. Okay. Now, we have two sets of variables, x and the worldsheet metric h, similar to the third action principle that we had for the particle. And therefore, we have two equations of motion. The equation of motion for the string coordinates x is given by formula 31. That will look a bit complicated if you have seen this before, but as remarked here in formula 33, this equation is the two-dimensional wave equation, but now on a curved surface with a metric h alpha beta. You can rewrite it in a form which is covariant with respect to worldsheet coordinate transformations using covariant derivatives or the Levi-Civita connection with respect to the worldsheet metric h alpha beta. And then you recognize that everything combines to give you the covariant version, the generally covariant version of the wave operator. So again, a wave equation, but now with a curved metric. And we will deal with this later. But let's also have a look at the second equation. This equation is the equation of motion for the worldsheet metric h alpha beta. And if you look at formula 32, you see that the worldsheet metric only enters algebraically. And that is telling us that the worldsheet metric does not have an independent dynamic. It's an auxiliary field. And what we can then do with such an auxiliary field is we can try to eliminate it. Well, we cannot completely solve for it, but we can derive the relation 34 between the intrinsic metric and the induced metric. And this equation is good enough to eliminate h from the Polyakov metric, from the Polyakov action, and I claim the result that you then get is a number go to action. And this tells us that the two actions are equivalent. So what effectively we have done by introducing the Polyakov action is we have introduced one extra auxiliary variable and rewritten the action in a way which is nicer, because now we have gotten rid of the square root that makes a number go to action a bit cumbersome to work with. Another advantage of the Polyakov action is that we can now apply a different perspective. We have a second independent way of thinking about what is going on. Normally, we say what the action describes is a string moving in a d-dimensional Minkowski space, but we can, due to the standard field theoretical form that this Polyakov action has, we can turn the logic around and read this as, we can read sigma as a kind of two-dimensional space-time on which we have a bunch of scalar fields which happen to take value in a special type of target space, which is Minkowski space. So that is the reading as a two-dimensional sigma model. Sigma models are models of massive scalar fields which take value in some space called the target space. In our case, the target space of our two-dimensional field theory happens to be d-dimensional Minkowski space, and therefore we can read this two-dimensional field theory as describing the motion of a one-dimensional extended object. Now, this really helps us to bring in concepts and intuitions from field theory, and this time two-dimensional field theory. So what are important concepts in field theory? Well, one standard concept is the energy momentum tensor. We can now compute the worldsheet energy momentum tensor. There's several ways how you can define an energy momentum tensor in field theory. If you are living on a curved space like our worldsheet sigma, the natural way to define the energy momentum tensor is to define it as the response of the action under an infinitesimal change of the metric. And this is indicated here. So how one then computes T alpha beta is one takes the Polyakov action, one replaces the worldsheet metric by worldsheet metric plus an infinitesimal piece, Taylor expands everything to linear order, and then reads off the variation of the action. And this is the right-hand side of formula 37. Now, coming back to our string theory point of view, of course, the equation of motion for H alpha beta is then T alpha beta is equal to 0. This is, and we are encountering this again, a constraint which we need to impose on top of the field equations, which in our case is the two-dimensional wave equation with the metric H. Good. So T alpha beta is this constraint that we have to impose, but there's more to learn. Maybe before I come to this point, I indicate the situation with another drawing, because we need to think properly about what these constraints are. So here in black, I've tried to indicate the space of all possible configurations. In blue, we then have the solutions to the equations of motion, but we also have to impose constraints, which are another surface, subsurface in the space of all configurations. And what we then have to pick are those solutions which are also solution to the constraints. Now, what should be clear from this picture that even if the constraint surface takes the form T alpha beta equals to 0, because this is just a subspace of the configuration space, I can still get information by looking at derivatives of T alpha beta. And derivatives of T alpha beta also have an important meaning. Let's check where I am. have an important meaning. Namely, they are related to two-dimensional energy momentum conservation. Energy momentum conservation means that the divergence of the energy momentum tensor is equal to 0. And if we are on a curved worldsheet, we have to take the covariant derivative. So the covariant divergence of the energy momentum tensor is equal to 0. Now, this equation, 38, you can verify, but if you verify it, you will find that you need to use the equations of motion. So this conservation equation only holds on shell on the locus in the configuration space where the equations of motion are satisfied. Good. Now coming back to these Weyl transformations, these Weyl transformations, just to remind, consist of multiplying the worldsheet metric by an everywhere positive function. And it's important to note that this does not act on the coordinate sigma, but it's an extra transformation where we just take the worldsheet metric and multiply it by a function. So it's an independent transformation, which is local in the sense that it depends on the coordinate sigma. You could, of course, write down d-dimensional versions of the Polyakov action, and in particular the point particle action that we wrote down at the end of the last lecture was a one-dimensional version of this. But I claim if d is not exactly equals to 2, these actions will be reparametrization invariant, but not Weyl invariant. And that's what, again, makes string theory special. We have an extra symmetry, the Weyl transformations, whose importance we will learn to appreciate further down the course. One thing I can already say, related to the invariance under Weyl transformations is a special property of the energy momentum tensor, namely the energy momentum tensor is traceless. To be precise, it is traceless as a tensor. It's slightly different from traceless as a matrix, because we want to make a covariant statement, and that means trace of a tensor is defined by its contraction with a metric. Given this, you should be able to verify that the expression I gave you for the energy momentum tensor is indeed traceless. And this condition now holds without using the equations of motion, so it is off shell. So what we know so far about the energy momentum tensor is it is traceless off shell and conserved on shell. And those are things that we will need to use in order to deal with our constraints. So we have reparametrization invariance in our theory. And one way of using reparametrization invariance is to use a particular parametrization of your theory, which is as simple and as convenient as possible. In the jargon, this is then also called choosing a gauge. Now, what is the gauge that makes our life as simple as possible? We can use a mathematical fact, namely any two-dimensional metric is conformally flat. Conformally flat means the metric can always be written by applying a coordinate transformation or reparametrization as the standard flat metric multiplied by a conformal factor or nowhere vanishing positive function. This is what it means to be conformally flat. And this statement holds both in Lorentz signature, but also in Euclidean signature, where it is often part in, say, a course on complex functions. Good. So by reparametrization, we can take our worldsheet metric and bring it to this conformally flat form. But, and here we can see for the first time why the Weyl transformation is also extremely useful. Since we also have Weyl transformations, we can use them to even eliminate this conformal factor and then choose our worldsheet metric to be just the flat Minkowski metric. And this is what is called the conformal gauge, and it's clearly the gauge which will make our lives as easy as can be. As a cautionary remark, this form of the conformal gauge applies locally on the worldsheet. If we have a worldsheet which is not just a strip or cylinder, but more complicated, then this choice is possible locally, but not necessarily globally. So there is then further technical complications, which, however, will not enter in what we have to do in our course here. And the remarks that I have also tabulated here just emphasizes the importance of the Weil transformation. The reason why we can transform our worldsheet metric to a flat metric is that we have as many local transformations as the worldsheet metric has independent components. The worldsheet metric is symmetric, hence it has 3 independent components, and we have 3 independent local symmetries. We can reparameterize 2 coordinates, and we have, as our joker, the Weil transformations. Okay, let us then see what the benefits of the conformal gauge are, quite explicitly. The metric becomes the 2-dimensional Minkowski metric, which is nice. The equation of motion just becomes the standard 2-dimensional wave equation, which is really great because now from D'Alembert, we immediately know what the general solution is. Namely, the general solution is a superposition of independent left and right moving waves, meaning we have 2 independent functions of 1 variable each, and the variables that we have to take are sigma 0 plus sigma 1 and sigma 0 minus sigma 1 to describe left and right moving waves. So that is a general solution. Of course, we are not done then. We have to impose boundary conditions, and we have the same choices as we discussed for Nambu-Goto, namely periodic Neumann and Dirichlet. And then we have to impose our constraints, T alpha beta equals to 0. Yeah, here I write there are 3 independent conditions because the energy momentum tensor is symmetric and has 3 independent components. But we have already seen that the tracelessness holds off shell, and therefore we actually only have 2 non-trivial conditions to impose. One is the vanishing of the off-diagonal elements, and one is the vanishing of the diagonal elements, which by tracelessness are equal to each other. And we can also express this in terms of the tangent vector. So these are the constraints that we have to impose. Since we are reaching the end, let me see what is a good point to terminate for today. Yeah, here's a suggestion. Given also conformal gauge, if you're not so familiar with covariant derivatives, instead of checking the conservation equation for the energy momentum tensor with a covariant derivative, you can check it with a partial derivative, but will still need to use the equation of motion. For the tracelessness, it does not really make much of a difference whether you have a general metric or the 2-dimensional Minkowski metric, but for the energy momentum conservation equation, it is a simplification if you do it with a partial derivative. And I think that is actually a good time to stop. Let me check. As I can see the chat. Okay, so there were no remarks, and apparently also nobody put in something into the chat, but maybe as is a good point for me to stop sharing and giving you the opportunity to ask questions if you like. Or I can ask you a question. Is the speed at which we are currently going with the lectures okay, or is it too fast or too slow? Please feel free to unmute yourself and make a remark or put something into the chat. Okay, I see no reaction, so I suppose that seems to be okay. Of course, you can also communicate with me by email, or you can post something on our nice course forum, which I will check not every day, but from time to time. Okay. did I miss a slide? The conformal symmetries are just before the Polyakov strings. Okay, I can quickly check this. Thank you for your question. Okay, let me. Yeah, I think I might have, yeah, right. I did not talk over this slide, so let me just check briefly on what I would have commented here. Good. Yeah, maybe we will come back to this anyway in the next lecture, but let me stress the following. The conformal gauge is to say that the metric is the two-dimensional Minkowski metric. But this is not a complete gauge fixing for the following reason. Suppose we make a worldsheet reparametrization, but we show this in such a way that the worldsheet metric, which is a tensor, is only changed by a conformal factor or by multiplication, which with an everywhere positive function. If we restrict ourselves to such reparametrizations, then we can remove the factor that we produce by the reparametrization by a Weil transformation, and then we are back in our conformal gauge. That means that we retain a residual freedom to make reparametrizations which are so-called conformal transformations, meaning these are transformations which only change the expression for the metric by a conformal factor. And therefore, when we work with string theory in the defined by the Polyakov action and impose the conformal gauge, we have a special type of two-dimensional field theory, namely a conformal field theory, and that will indeed be a major topic in a kind of the middle part of the course. So technically, we'll have 6 parts, and parts 2 and 3 will develop conformal field theory aspects of string theory. Okay, good. I think we are over time. So suppose that's all that we can do today. Thank you very much for joining us today. Any further questions, please use email or the course forum. And otherwise, we meet again next week, same place, same time. I'll hang around until everybody has gone, but that's now the official end. So see you next week.